So what is a state machine? The state machine, first of all, normally it has nothing to do with blockchain in particular. So it's just some sort of system. You start in a certain state, and then there are one or more transitions to other states. And so you can transition from the initial state into this one or that one, and that goes on. So basically it's just a directed graph. And then there may also be some states that are special in that they are so-called final states, from which there are no possible ways out anymore, no transitions that lead out of the final state. And what does that have to do with blockchain and with our examples? So if we look again at the diagram we had earlier for how our game works, then we can consider that a state machine. So the initial state would be this one here, where the first player has made the move, and the state is basically characterized by this datum, by the hash. And in this state, there are two possible transitions. One where the second player plays, Bob plays, and the second one where it doesn't play and the first player can reclaim. So all the nodes in this diagram correspond to states, and all the arrows, the edges of the graph, correspond to transitions. And in particular in the blockchain, the state machine will be represented by UTXO sitting at the state machine script address. And the state of the state machine will be the datum of that UTXO. And the transition will be a transaction that consumes the current state, this current UTXO, using a redeemer that characterizes the transition and then produces a new UTXO at the same address, where the datum now reflects the new state. So that's the relation. And that fits a lot of situations very nicely. And there is special support in the Plutus libraries to easily implement such state machines. And we will see when we use this approach that our code will be much shorter. The support for state machines is in package Plutus contract in the module Plutus contract state machine. And let's first look at what a state machine is. So a state machine has two type parameters, S and I. That stands for state and input, and that corresponds to datum and redeemer. So in the actual implementation and the manifestation of the state machine on the blockchain, S will be the datum type and I will be the redeemer type. And so a state machine is a record type with 4 fields. So the most important one probably is the transition that defines from which states, using which transition, you can change into another state. And this state S type is defined here. So that is basically the datum, the state itself, and also the value. Remember I said that this will be represented, the state machine will be represented by a UTXO. So the state of the state machine is a UTXO, and that has a datum and a value. So we have access to both in this state type. So given the state type, so the present datum and value of the UTXO, and a transaction that tries to consume this UTXO with the redeemer I, we can indicate that this transition is not allowed by returning nothing in this function. And if it is allowed, we return a tuple, and the second component is the new state. So this transaction will consume the existing UTXO and produce a new one at the same address, and this here will be the new datum and value of the new output, the new UTXO. And then we can have TX constraints that until now we've only seen in off-chain code that specify additional constraints that the transaction that does this transition must satisfy. So that's the transition function. Then we have a function, just a predicate on datums, basically on states, that tells us whether it's a final state or not. So final states are special in that in this transition function, if we transition into a final state, then there mustn't be any value attached with it. And then this output that normally gets produced, so we normally consume the UTXO representing the old state and produce a new output representing the new state. But if this new state is final, then we don't. So then we don't produce a new UTXO. So basically the machine end state stops. So that's this SM final. SM check is very similar to this transition function, except it doesn't have the value. So it just gets the datum and the redeemer and the context and returns the bool. So this is basically an additional checks that can't be expressed in terms of these TX constraints. Finally, we have this SM thread token, which can or cannot be there. And the purpose of this is to solve the same problem that we already had with our Oracle in the last lecture and also now with our game, that as I have said many times before, you can't stop anybody from sending anything to any arbitrary address. So there can be many UTXOs sitting at an address that you have no control over. But in cases like these, like the game in the previous example, we want to identify a specific UTXO. And the trick we used just now was to mint an NFT and insist on it being present in the UTXO. And because an NFT by definition can only exist once, this allows us to pinpoint the right UTXO and ignore other UTXOs that may sit at the same address. And the thread token here serves the same purpose. So if we look at thread token, it is basically a reference to a UTXO and a currency symbol. And this UTXO will be the one that uniquely identifies the minting transaction of the NFT. So this is like a weird way to specify an NFT. So we don't have to use this mechanism, but if we use this, so if we put a just thread token there in the state machine, then the mechanism will automatically take care of minting this NFT that corresponds to this thread token and then threading it through the state transitions. So in all these checks in validation, it will always make sure that the corresponding NFT is present in the UTXO. And also, if it's not a final state and there is a UTXO at the same address in the output, that this NFT will then also be present in that output. So we don't have to worry about that. That will automatically be taken care of. The minting and eventually burning in the final state of this NFT that corresponds to this thread token will be handled automatically. And it also doesn't appear in the values. So we said here the state bundles the datum and the value. And of course, this NFT will be part of the value, but it won't be visible here. So we can ignore that. We don't have to worry about it. I have rewritten the game using the state machine mechanism in module week 7 state machine. And the beginning is very similar. So I again have this game type. Most fields are exactly the same. So the two payment pub key hashes of the players, the stake in Loveless, the two deadlines. The only difference is earlier the token was of type asset class because I myself implemented this NFT thread token mechanism. Now that we're using stake machines, I use type thread token instead. Game choice is the same. This is all the same. Game datum has slightly changed because I have added a second constructor that are called finished that we didn't need before, and that is supposed to represent the final state of our state machine. So it won't correspond to a UTXO, but we need that for the state machine mechanism to work. So the first constructor is as before, hash provided by the second player may be hash provided by the first player may be made by the second player, and then this additional constructor to represent the final state that the game has ended. That makes the definition of equality slightly more complicated because now I have to take this second constructor into account as well. But nothing serious going on there. The redeemer is exactly the same as before. These two helper functions are exactly the same as before, and now this is now the transition function of the state machine, which sort of corresponds, as we will see in a moment, to the make game validator that we had earlier. So this is basically the core business logic. And so it takes the game, the parameter, and now, as we saw in the definition of state machine, state datum. So remember, that's a pair basically consisting of the datum and the value and the redeemer, and then we must return nothing if it's not allowed, and just a pair of new state and constraints on the transaction. Now let's try to compare the transition function of the state machine to the make game validator function of our first version of the game. So the first thing, I mean, of course, the signature is different, but in spirit, it's a very similar thing. So in both functions, try to determine whether basically a combination of datum and redeemer and transaction is valid or not. So we will see the correspondence now. The first difference we notice is here in our old version, we first had to check that the input we are consuming, the UTXO we are consuming, actually carries the NFT. And that is missing in the state machine formulation because the state machine mechanism automatically takes care of that if we set this last field in the state machine to some thread tokens. Then the mechanism will automatically check that the NFT is present in the consumed UTXO and also in the newly created UTXO, if it's not a final state. So let's look at this first case where the first player had moved. So the component for the second player was still nothing, and now the second player wants to make a play with choice C. So we check these 6 conditions here, and let's see how they are reflected in the state machine formulation. And in the state machine, we have this state S, which remember is a combination of datum and value, and you can access those two with state value and state data. So state value S is now the value in the UTXO that we are consuming. State data S is the datum, and R is the redeemer. So we have this triple. And here I check that the value is actually the stake of the game. So the value contained in the consumed UTXO. And that's the condition that was the second condition that we checked here. Now the result of the transition function, recall, if it's valid, it's just a pair. And the first component of the pair is constraints on the transaction, formulated using this constraints module that we know from off-chain code. And the second component of the pair is the new state of the resulting UTXO, which again is given by datum and value. So here we are specifying with this transition, if the second player makes a move, the new datum will be BS just C, and the new value will be twice the stake of the game because it's now the first player stake and the second player stake. We leave the NFT out of here, even though it should be present in the UTXO. And that is again because the state machine implicitly takes care of that NFT, that it's passed through. So we don't mention it here. So now let's go through these 6 conditions and check how they are reflected in the state machine formulation. So the first one, that the transaction has to be signed by the second player. That reflects here with the must be signed by constraint. The next one was that the value of the input is the stake of the game. As I mentioned before, we check that here on the left-hand side. So we only consider this whole case if that is actually true. The third one is that the output value must be twice the game state. That is reflected here in the second part of this tuple that we return. That's the new value. Then we checked that the new output datum is the old output datum, where now the nothing has been replaced by just C. That is reflected here in the first component of the state tuple that we return. Then we check the deadline so that this move is made before the first deadline passed. This is given here by the second constraint. Must validate in to play deadline game. And finally, here we check the token that the NFT was present in the output, but as I just explained, we don't have to check that in the state machine formulation if we make use of the state token mechanism. Okay, so that's the first case. The second case was the one where the second player has moved, which is reflected here in the just, and the first player realizes he has won and now wants to reveal his nons in order to prove that he has indeed won. So let's see what conditions we had here. First one, this must be signed by the first player. This is here in this constraint. Second one, we must check this nonce, and that is something we can't formulate as a constraint. So we leave that out here, so that's missing, and we will come to that later. There is this escape hatch in the state machine mechanism where you can still put conditions on, even if they can't be expressed in terms of constraints. Third condition here was the validity interval. So it has to happen after the deadline. This is here the second constraint. Then we have the condition that the input value must be twice the stake. That we check here on the left-hand side already. And finally, we check here that the NFT goes to the first player. But this is different in the state machine because the way it works is that this thread token is minted when you start the state machine, and it's burned when you stop it, when you reach a final state. So this is a bit different here. We don't hand the thread token back to the first player, we burn it instead. So this condition is missing, and that's implicitly taken care of. Now for the final state here, we transition to this finished state, which, as I said before, doesn't correspond to a UTXO. So we will later define that this finished state is final state, which means that the state machine mechanism will then not create a new UTXO at the same address, and instead basically stop the state machine, burn the thread token. So then no value is left in the contract. Now the third case was the one where the second player simply doesn't move in time before the deadline. So the first player wants to reclaim his stake. First condition is the transaction must be signed by the first player. We have that here in this constraint. Second condition about when that's supposed to happen. So it must be after the deadline has passed. So that's this constraint. Then we check the input. It must be the state, the stake. So we check that here on the left-hand side. Again, this NFT to first is different now because we burn the state or the thread token instead, but that's implicitly taken care of by the state machine. So instead, all we have here is that we again transition to this final state where no value is left in the contract. Now the last case is the one where the second player has moved and the first player then doesn't reveal, either because the first player has realized he has lost or because he left the game for whatever reason. So we check that this has to be signed by the second player. This is reflected in this constraint. Then the deadline, it must happen after the reveal deadline. This is here, this second constraint. Then the input must be twice the stake of the game. Again, this is checked here on the left-hand side. And again, same story, NFT to first goes away, and instead we just let the state machine mechanism take care of that and transition to the final state. And as here we said that all other combinations are invalid, so here we say all other combinations, we return nothing, which corresponds to the same thing. So the conditions themselves are maybe not really shorter than in the old version, but we don't need any helper functions. So this in, out, own input, own output, and so on, we don't need. This is all taken care of by the state machine or by these constraints. And we don't need to worry about the NFT. That's also automatically taken care of. So this is already significantly shorter than in the old version. But we are not done yet defining the state machine. There were other fields in the record. One is final, so we must specify what final states are, and that's just this finished state. So final finished is true and everything else is false. Then we left out the nonce check in the transition function because we couldn't express that as a constraint. And that's exactly what this check function is for. We have two auxiliary arguments, these two byte strings that we also had in the other version, 0 and 1, for the same reason we need that here. And then datum and redeemer and context, and must just return whether this additional check is satisfied. We ignore the context, we don't need it here. And the only condition we have to put into this check function is the one with the nonce. And that was in the situation where the second player had played, just C, and where the redeemer is reveal nonce. And this line here is just the old check we had in the first version as well. We compute the concatenation of the nonce and the byte string corresponding to the move, hash that, and compare it with the originally provided hash. And all other situations, we don't need an additional check and therefore can return true. Now we can define our state machine, and so for now it has these three parameters, the game and these two auxiliary byte strings, and it returns a state machine. And we just provide the four fields that we just defined. So transition game, that was the important one, and this final check, the additional check, and finally the thread token, which we just take from the game value. Now there is machinery provided by the state machine to make a game validator. So what our old make game validator function can now be replaced by using the state machine and using the make validator game state machine. So game state machine is our state machine here, and there's a make validator function that turns that into something of this type, which is exactly the type we had before in our handwritten version. So this is similar to before. I mean, we had this other mechanism to bundle datum type and redeemer type. The state machine does the same basically. So now our type gaming can just be state machine game datum game redeemer, our two strings. And I provided a second version of game state machine where we only have to specify the game and not these two strings. And that won't work in on-chain code, so it doesn't have this inlineable pragma because of the literal strings here. But in off-chain code, it works perfectly fine, and then we don't have to provide these two additional parameters. Now this is exactly as before, so the same boilerplate we had before, except now this make game validator has been defined here using the state machine mechanism instead of doing it explicitly. And game address, game client, no, game address is the same. Game client is a new thing. Game client is a state machine client, and this is basically what we need to interact with state machine from our wallet, from our contract monad. If we look at the definition of state machine client, we see it has two fields, a state machine instance and then this chooser. So the state machine instance is again a record type with two fields, and it has a state machine and the typed validator. And both of those we already have defined, so we can make a state machine instance. So what's this chooser all about? Well, in general, if we don't use the thread token mechanism, the NFT mechanism, we could have several UTXOs sitting at the address of the state machine. And the chooser is a way to pick the right one. So in general, we will find a list of UTXOs. I mean, it's a different type here, on-chain state, but you can think UTXOs sitting at the state machine address. And this chooser is then a function given such a list, picking one. So either producing error or picking one of those. But there's a default implementation for such a chooser, which if we use the thread token mechanism, just picks the one UTXO that holds this thread token. So in order to make a state machine client, we can use the make state machine client function, which just takes a state machine instance. So not a chooser, because the default chooser will be used. So to make our game client given a game, we can just use this make state machine client, and now we need the state machine instance. and we must provide the state machine, for which we can use our game state machine prime with the game as parameter, and the type game validator we also have defined here. So this gives us our game client. And now the client can be used to interact with the state machine from off-chain code. First parameters are exactly the same. There's one small nuisance, that these state machine contracts that the state machine module provides, they use a specific error type, or they have a specific constraint on the error type. And one error type that works is SM contract error. But I want to do what I did in the last lectures and always use text as my error type. So in order to make those two fit together, I define this map error prime function, which uses the map error we have discussed before, and it turns an SM contract error into a text by showing the SM contract error and then packing the resulting string into a text. I also again have this helper function, wait until time has passed, that I already used in the even odd example, which, given a time, first waits until this time has been reached and then waits for another slot to make sure we are in the slot after this time. Now the first game becomes much nicer, much shorter, much more compact. It starts the same, so we look up our own public key hash. Now there's something new. We need to get this thread token. So we must identify a UTXO in our wallet that can be used for the minting of the NFT to make that a true NFT, as I explained in the lecture on native tokens and NFTs. So that's what this getThreadToken function does. And I have to apply the map error prime in order to convert it to text error messages, as I explained. And there is, in the documentation for this getThreadToken, it says you mustn't do any transactions after you have invoked that before you use it for a state machine, because that could change the UTXOs in your wallet. So then the situation could change. Okay, so now we have our public key hash and our thread token, and we can define the game using public key hash and thread token at the appropriate spots and taking the rest from the parameters we got. Now we can define our game client using the game client function. These three are as before, so it's the stake, our choice, and the hash that we reveal, that we commit to, that we use to commit to our move. And now in this one line, a lot happens under the hood. So this run initialize, given the client a datum and a value. First, it will mint the NFT corresponding to this thread token. And then it will create a UTXO at the state machine address to start the state machine, put the NFT in that UTXO to uniquely identify it, and the datum and value of that UTXO are given by these arguments here. So we put it in the initial state we want, where the first player commits using this hash, and the second player hasn't moved yet, and the first player puts down his stake. And again, we have to use the map error prime in order to adjust the error messages. And we just log that we made the first move. Now, this is also new, and if you look at the type, this has also slightly changed. Earlier, I didn't use the tell mechanism, the writer mechanism of the contract monad. Now I need to communicate the thread token, because the second player wants to find the game. So the second player must define this game, and part of that game is this thread token. So the second player otherwise would have no way of knowing what the thread token is. So in order to communicate that, I tell it here. Okay, so this is all to set it up. And now if we recall, we have to wait, and then we needed this helper function find game datum or game output in order to, after we have waited for the second player to move, to find the UTXO again. This is now much simpler because we can use something called get on-chain state. So get on-chain state takes the state machine client and returns maybe a pair of something of type on-chain state and a UTXO map. So the UTXO map will be consisting of all UTXOs sitting at the state machine address. But for our example, we can ignore that. So the on-chain state, let's check that out. That is basically a pair consisting of something of type typed script tx out and typed script tx out ref. So what's this typed script tx out? If we check that, then we see that in turn is also a pair consisting of a usual tx out and a datum. So normally a tx out does contain a datum or a datum hash, but of just type datum. So the value actually of the datum is built-in data. And then recall if we wanted to get our type datum out of that, we always had to try to deserialize it, and that could fail and so on. So the difference to normal tx out with this typed script tx out is that this has already been done for us. So in our case, date A will be our state machine type, our gaming type, and datum type will then be game datum. So this is more convenient, so we immediately get the datum out of that. So by using get on-chain state client, we have this M, and this M, it could be nothing if no output is found. As before, this should never happen, but if it does, we throw an error. And now we get this on-chain state. We are not interested in the reference, only in the O itself. And then we use this ty tx out data O to directly access the datum. So no need to look up hashes. That's all somehow wrapped in this ty tx out data. So now we immediately have the datum. And as before, we have the two cases that the second player hasn't moved or that it has moved. So if it hasn't moved, we must reclaim. And earlier then we had lots of code to set up the lookups and the constraints that we need. Now we only need this line. So the important function here is run step. So run step creates a transaction and submits it that will transition the state machine. And it takes as input the client again, and then simply the redeemer. That's all. All the input we need is the redeemer. And then we will get this transition result, and I'm not using that in this example, but that basically encodes whether it failed and for what reason it failed, or whether it succeeded, and if it succeeded, what the new state is. But I don't really need this in this example. So this is all. This is really dramatically simpler. So all I have to do is I tell it, okay, in this case, the second player hasn't moved. I just do a step with the claim first redeemer. No constraints, no lookups, no submissions or waiting. This is all handled by the run step. And this is really neat, I think. This is dramatically simpler than before. And the way it works, of course, is that in the transition function, these conditions use these constraints. So all the constraints are available to the state machine mechanism, and that allows it to handle all of this automatically and to automatically assemble compose the transaction that is needed. So this is where the state machine approach really plays out. So basically it's just this one line. And in the other case where the second player has moved, and if we think we won or if we know we won, again, now we have to reveal, and it's just this one line. So again, run step client with the reveal fp nonce fp redeemer. And that's all. No constraints, no lookups, nothing. So this is much simpler now. And we don't need any helper functions as we did before. And same for the second player, it's just as short. So second game, the beginning is the same. We look up the public key hash. We define our game parameter. We define the state machine client. Then we use this get on-chain state again to check or find the UTXO that represents the state machine, represents the game. If we don't find it, that means no game is running. If we do find it, all these other pieces of information we could use, we don't need, only the O. And again, we use this typed version to grab the datum. And this case would mean that we haven't played yet, so now we should play. And other cases are unexpected. So we expect that we can play. And in order to play, again, it's just one line of code. We use run step and then the play our choice redeemer. Then we wait as before until the reveal deadline has passed. We again check the new state, and now if there is none, that means the first player has won, so we don't do anything. But if there is something, it means the first player hasn't won, and again just one line of code to claim our win. And that's it. So here it really shines, the state machine approach. It was already, I think, a bit shorter here in the on-chain code, a bit more concise. We needed, particularly we needed less helper functions. We didn't have to worry about this handling of the own input, own output, and of the NFT that it's passed through. But in the off-chain code, it's really dramatically simpler now and much more readable. And the rest is exactly the same. That's just copy-pasted. And what is particularly nice about the state machine approach is that we don't have to replicate logic anymore. I mean, earlier I explained that the on-chain validation checks whether a transaction is valid, whereas the off-chain code has to construct a transaction that then will pass these checks that validation does. So on-chain and off-chain logic has slightly different purposes. On-chain has to check, whereas off-chain has to construct. But by using this trick to specify the state machine using the constraints that can be used for both, for checking and for construction, we now don't have to replicate this logic anymore. So we only use the constraints, and they can be used to construct the transaction, but also to check the transaction. So in principle, we halve the amount of code we need to write, and we remove a lot of duplication. In order to test this, I created a module called Week 7 Test State Machine, which is extremely similar to the test even odd module I showed you earlier. Of course, instead of even odd, I'm importing our state machine module here. Then it is simpler because I don't have to specify an initial state. Remember, I had to do that for testing the even odd module because I needed this state token, this NFT. So I had to specify that the first player owned it in the beginning. Now with the state machine mechanism, the thread token mechanism, that is taken care of automatically. So the token is minted when we initialize the state machine and then burned when we reach a final state. So I can use the default initial state, which runs with 10 wallets and gives every player 100 ADA. And because of that, I also decreased the stake from 100 ADA to 5 ADA. Earlier, I used the stake of 100 ADA, but there the two wallets that I was using both had 1,000 ADA each to begin with. Then there is one difference that's a bit unpleasant. In the other test module, in the other emulator trace, I use slot to begin POSIX time here. Now I have changed that to end POSIX time. And that's a bit unfortunate, and it's due to something I mentioned before when I talked about time. Remember, Plutus uses POSIX times, which is of course convenient because that's real time and you don't have to worry about slot length and you don't have to worry about future protocol updates that might change the length of a slot. The blockchain, however, Ouroboros, uses slots. So when you go from Plutus to the blockchain and back, you always have to convert. And because a slot is coarser than the unit of POSIX times, which is milliseconds, slot is 1 second and millisecond is only a thousandth of that. that can't be a faithful conversion. So if you go back and forth, I mean, if you start with a POSIX time, convert to a slot, you lose precision basically. And then if you convert back to POSIX time, you don't necessarily end up with the same time you started with. And that unfortunately has the effect that if you use constraints with time must validate in, what I said earlier is not strictly speaking true. So earlier I said by using the state machine mechanism and the transition function that uses the constraints, you automatically are guaranteed to have off-chain code that makes the on-chain validation pass. So that's the idea of this constraint mechanism, right? That the constraint can be used both for checking validity in the on-chain part and for constructing a valid transaction in the off-chain part. So of course they should perfectly match. So if you have a constraint must pay to pub key, for example, then that will be checked in the on-chain part, and the off-chain part will make sure that the transaction that's being constructed indeed has an output that pays the specified amount to that public key. And of course, you would expect the same for this must validate in constraint. So the on-chain part checks that the transaction is actually submitted in the correct interval, time interval, and then the off-chain part must construct a transaction that has a correct time interval. But due to these conversion issues, the imprecision, the unfaithfulness of the conversion between slots and POSIX time, this doesn't always work. So there's a problem. So if I had used begin POSIX time as before, then the state machine off-chain code would have constructed transactions that then wouldn't validate, which is not nice, but it can't be helped, I'm afraid. But I can fix it by using the slot to end POSIX time instead. So you have to be careful when time is involved. Apart from that, it's exactly the same code. So it's just simpler because I don't need the initial state. And I, as I said, changed the stake and I slightly changed the deadlines here. But the rest is exactly the same. So in order to test that in the REPL, you can use the same as before. So for example, both players choose 0. So the first player should win. We see there's indeed one player who has almost won 5 ADA and another one who has lost a bit more than 5 ADA. So the discrepancy to 5 is again due to transaction fees. And so we see this wallet here, 87 must be known wallet 1, and this one, 7CE, must be known wallet 2. So if I change the second choice, then it should be reversed. And indeed, now this 7CE wallet, the second one, has gained almost 5 ADA, and the first one here has lost a bit more than 5 ADA. And we see another nice effect of the state machine mechanism in this example, that this unfairness I moaned about before is gone. So now when the second player wins, he doesn't have to deposit these 2 ADA to pay back the NFT to the first player. And that is due to the fact that the state machine handles this thread token slightly differently to how I handle the NFT. So I said it should always, in the end, go back to the first player. Whereas, as I explained, the state machine mechanism burns the thread token when a final state has been reached. So because it's burned, no deposit is necessary to hold this token. And that makes the game fairer, which is a nice side effect as well. So state machines are not always appropriate, but when they are, you should definitely use them because they dramatically reduce the amount of code you have to write and also remove sources of error because you avoid code duplication. Basically, the state machine automatically takes care of guaranteeing that the on-chain and the off-chain code fit together. So the off-chain code will produce transactions that then will be validated by the on-chain code. And until now, we always had to take care of that by hand. So a big source of errors or bugs is removed. And everything is much shorter. because a lot of the machinery to identify the right UTXO and to pass through the state token is taken care of for you automatically by the state machine mechanism. Of course, it's not always appropriate, but when you have this model that there's basically one specific UTXO that carries some state in its datum and that transitions, so there are transactions that consume this UTXO and produce a new one at the same address with a possibly updated datum and value, then you should definitely ask yourself whether you can model that as a state machine and then use this state machine mechanism. However, as I said before, in practice, they haven't really been used yet. And the reason is that the state machine mechanism, as it is written now, has a lot of overhead. So it increases the necessary resources to run the validators and minting policies. And that is a problem because resources are quite limited at the moment anyway. So sometimes one has to work relatively hard to write a validator or any Plutus that is small enough to fit into these resource limits. So the overhead caused by the state machine mechanism sometimes pushes validators over that limit. But the Plutus team, as I said before, is working on making everything more efficient and optimizing everything. So hopefully very soon these state machines will be practically useful and can be used in real world DApps. And therefore, I think it's certainly a good thing to know about them and learn about them. And conceptually, they are just so beautiful because they really make the code much simpler and more concise and remove a lot of common causes for bugs.